Thanks, Barry. Thanks, both for the organization and for the invitation. So I'll be talking of LEOs and GEOs, but really it's LEOs and non-geostationary, to be honest. So let's start with GEOs. With the GEO system, by definition, you need one satellite to cover a region. As Arthur C. Clarke has shown a long time ago, I think it was 45, you can have a quasi-global system with 3 satellites. With a GEO system, you can have demand profiling. So you can put more capacity on one area and less capacity on another area as required. And you can also assign capacity dynamically. So if one area has a peak, you can put more capacity in there. If it is not being used, that capacity can put somewhere else. However, one major handicap of GEOs is that polar regions cannot be covered. When it comes to the terminals, GEO systems require what I would call a simple, powerful terminal. And what I mean here is typically for a residential HTS system, we're using 70-centimeter dishes. No pointing. GEO by definition is fixed. Of course, if it's mobile, pointing has to be included. Geostationaries tend to be reasonably far away with a round trip delay of 250 milliseconds. And therefore, that is a component of latency. And therefore, the latency cannot be too low. It cannot be below 250. Time to market is relatively short, typically about 4 years. And the number of satellites that is required is 1, with a lifetime typically of 15 years. That's 15 years design lifetime, and typically you can get 20, even more operation lifetime out of them. You need 1 launcher, but it's a heavy launch. Typically more than 6 tons, 6.4 tons is quite typical. So the initial cost is more or less equal to the cost over 15 years, the lifetime of the satellite. And it's a few hundreds of millions of euros. If we now look at LEOs, you need a constellation if you want 100% time and area coverage. They can be truly ubiquitous, truly global. They tend to provide a homogeneous service symmetrical about the equator. And dynamic capacity allocation is not easy in my view. This is because if you have a satellite that's over the ocean, you cannot put that capacity somewhere else if it's not required. When it comes to the terminal, you need what I would call a complex low power terminal. Basically, you have a free space difference if we consider 550 kilometers as the altitude of LEO. Compared to GEO, there are 36 dBs of free space loss advantage. The satellites are smaller, so there's less DC power available and therefore less RF power available. And the antennas are also smaller, so you can't use the 36 dBs for the terminal, but the terminals can still be smaller and lower power. By definition, you need to track the beams as the satellite are whizzing above your head. And you need to at least have the capability to cover 2 beams so that you have 1 active and 1 in standby, so to speak. For 550 kilometers, the round trip is 4 milliseconds. So latency is improving there significantly. The time to market is relatively long because you need to produce many satellites, although they're produced quite rapidly, but launching is always a bit of a bottleneck. And if we consider a 15-year span, you typically need 4 times the number of satellites in the constellation. If we consider the lifetime of a satellite in LEO to be 5 years, you need to have the full complement available at T0. And then you need to update the satellites, replenish the satellites as you go along. So that makes it 4 times. The mass of the satellites, we're talking of hundreds of kilos. The initial cost is considerably higher. We're talking of a few billions, say 10 billion. So over the lifetime of the satellite, it becomes, over the 15-year lifetime, that would be 4 times that amount. We consider capacity density. With GEO, if we consider Europe or CONUS, that's 10 or 8 million square kilometers. So if we consider a terabit GEO system, a terabit VHTS, then the average capacity is between 100 and 120 kilobits per second per square kilometer. If we go to LEO, we consider a global coverage. The Earth's surface is 510 million kilometers squared. 28% of that is land, and 95% of the population lives in 10% of the area, or 2.8% of the Earth's surface. So basically, 2.8 of the capacity is available for 95% of the population, and the remaining capacity is available for the 5% of the population. Now, that model is a bit residential centric, because beyond residential, there's also aeronautical services, maritime, and governmental services. The model, as you can see, is a bit simplistic, but it highlights some of the challenges that we face with the LEOs, specifically in the technical, industrial, financial, and operations channels. If we now look at capacity costs, if we consider a GEO system, we take $700 million for one satellite at 1 terabit. The satellite is the system, so it's the same capacity. That brings the space capacity cost to about $700 per megabit. We can assume 100% fill factor, because we're assuming that there's enough flexibility to make sure that all the capacity can be used. So the sellable capacity cost is $700 per megabit. If we now consider a LEO system, and I've taken SpaceX as the example here, $10 billion, 12,000 satellites, 20 gigabits per satellite, so that the system capacity is 240 terabits. That brings the system capacity cost to $40 per megabit. However, as I said before, you may have problems selling all that capacity. So what I tried to do is I worked backwards, so to speak, to have a sellable capacity cost of $700 per megabit. You need to use at least 6% of the capacity. A conclusion of this could be that where you have the population, the 2.8% of the area and 95% of the population, and where you don't have the population densities, the two are should be more or less of the same order of magnitude in terms of capacity requirements. Again, this is highlighting some GEO issues. What is the sellable portion of the capacity? Issues with replenishment costs, ramp up on a global business. If you trying to open a market on a global basis, that's going to take time. And also the regulatory issues to be operational in all the countries you want to be in. Latency. So perhaps 5G has brought latency to the forefront. It pushes latency to milliseconds for certain applications like ultra reliable low latency communications, enhanced mobile broadband, and the control plane. We're talking here of 1 millisecond, 4 milliseconds, and 20 milliseconds for each one of those. We did say that the round trip is 250 milliseconds, but oddly enough, GEO can contribute to lower the system latency. If we consider that that GEOs can make contents available at the edge node, this is the edge computing, then by caching data closer to the user, contents can be delivered faster to the user when required. The broadcast function of satellites can make content available to a large number of edge nodes, and VHTS or HTS can make specific contents available to specific nodes, thus reducing the system latency. LEOs have a further advantage, even with respect to fiber. Fiber has a refractive index of about 1.47, which means that the speed of light in fiber is slower by that amount. If we take the example that we're seeing in the slide, we try to communicate between location 1 and 2. We have two options, either to have a direct fiber, which is shown in green, or a satellite link, which is shown in blue. If we consider a satellite altitude of 500 kilometers and the distance between the two locations of 2,500 kilometers, then the propagation time is more or less the same in both cases, 5.8 milliseconds. Now, if we take a link Paris to Moscow, that is almost 2,500 kilometers, so the advantage would be negligible. But if we have greater distances, like Paris to New York, or New York to San Francisco, then satellites will offer a better propagation delay performance. Thank you for your attention.